We're going to go through the recurrence relation mock paper over here. So 2 questions. Question number 1. A sequence is such that the first term u1 equals to p, where p is a constant, and un plus 1 equals to 5un over 8un plus 1 for n greater than or equals to 1. Part I, describe how the sequence behaves when p equals to 1. So when p equals to 1, right? Okay, you just work out this yourself. Okay, u1 equals to 1. Okay, when p equals to 1. Then u2 equals to 5u1 over 8u1 plus 1. So that is basically 5 over 9. Okay, you just work the rest out yourself. I'm not going to go through this. The sequence is a decreasing sequence because you can see from u1 to u5 is decreasing. And then after that, it will converge to half. So if you think about it, it's a pattern that you must observe. It's like you can see that, hey, 25 over 49 is close to 1. 125 over 259 is even closer to 1. 625 over 1245 is even more closer to 1. So that is how you describe the behavior. Okay, first thing, is it decreasing or increasing sequence or a constant sequence? Second thing, whether it converge or diverge. Now, part 2, find the value of P for which U6 equals to 3125 over 6253. So actually, right, okay, you ignore this statement over here first. So far in the video in the slides when I introduced this chapter to you, as well as in the previous practice questions, I introduced this chapter to you. What we have always been doing is the term after equals to the term before. So basically, the term before, right, X has the input for you to get the term after. Now, here's the problem in part 2, which quite a number of students in the past struggle. Now, what they want is, I give you the term after, U6, right? I want you to find the value of P, that is U1. So in short, I give you the term after, find for me the term before. But the problem here is this. In your equation over here, by writing the equation this way, is saying that given the term before, I can get the term after. So the term before acts as an input. But here's the problem. In part 2, they give you the term after. Then they want you to find the term before. Then how will you do in this case? Okay, ignore this statement over here. What we're going to do first is to make un the subject. Okay, I'm not going to go through the algebra over here. Okay, you're going to go through this yourself. Okay, I'm going to make un the subject. And then we arrive at this equation over here. Okay, for the algebra, you can pause the video if you're watching a recording. For the rest, you work on it later. So that's the algebra. Okay, and what we're going to do is, now that we have this equation over here, right? Then now this equation looks something that it looks like something that we can work with, because now is, as compared to over here, right, is given the term before, the input, I will get the term after, the output. So in this equation over here, given the term after, that's the input, I get the output, the term before. So that is something that I think I can work with, because I'm given the term after, I need to find the term before U1, which is the P I want to find. But hey, there's a problem. If you try to key this in your GC, you will notice that the GC always give the term after on the left and the term before. Okay, agree or not? So what you must do is, instead of writing as un plus 1 over here, you write it as un minus 1. Okay, what we are doing here is basically, first you make un the subject for such a question. So that your un over here is the term before, that's the output, taking the input, the term after. Okay, so in fact, what we are doing is, we are reversing the sequence. So all along, throughout my introduction of this chapter, as well as a practice question earlier, we have always been looking at the sequence from small to big. Okay, we have always been looking at the sequence from small to big. So now, instead of looking at the sequence from small to big, what I'm going to do is, for U1 over here, right, I treat it as, For U6 over here, I treat it as U1. For U5 over here, I treat it as U2. For U4 over here, I treat it as U3. For U3 over here, I treat it as U4. For U2 over here, I treat it as U5. For U1 over here, I treat it as U6. So basically now I reverse the sequence. I treat my U6 over here as U1. I look at the sequence in reverse. Okay, so how do I do that? Okay, very simply, we have already done it. Okay, by making un the subject such that the output is the term before and the input requires the term after, and then replacing the un plus 1 with un minus 1, what I'm essentially doing is, hey, let's reverse the sequence and look at it in the other direction. Okay, treating u6 as u1. So now your term after, right, has the term before. You see, the term after is the input, right? The term before is the output. So by replacing un plus 1 with un minus 1, this step actually just tells me that what I'm doing here essentially is I'm reversing the sequence. Now the term after becomes the term before so that I can key in my GC. You understand where I'm coming from? So that's the whole idea. Okay, I reverse the sequence. I treat the term after now as the input, and then I rewrite it as un minus 1 instead of un plus 1. So this way, I can key in my GC so that now the GC will be able to take in this equation. Okay, and then n min I set as 1 because I begin from u1. Okay, and my u1 over here is 3125 over 6253. So this is my beginning. So I reverse the sequence. Okay, now it will work. So that is the trick. I reverse the sequence. And then when I generate it out, you realize that, hey, oh, u1 is basically my 0.4998 is 3125 over 6253. And then what I have written just now, right? Okay, take a look here. Oh no, I should rewind it. Because I want to keep the answer clean, but okay, so what happens here is your U6, right, is now my U1. So I'm looking at this sequence here. Oh, wait, no. 1 second. Yeah. So originally, this U6 over here, right, is 3125 over 6253, agree? Now I treat it as the first term U1, 3125 over 6253. So my U1 over here is this U1, 3125 over 6253, understand? So originally U6 is 3125 over 6253 by the original sequence. So now I do the reverse, I treat U6 as U1. So U1 over here is 3125 over 6253. Understand? So now I reverse the sequence. So now my GC give me U1 is 3125 over 6253. And then U2, U3, U4, U5, U6. So U2, U3, U4, U5, U6 is 0.2. And this U6 over here would be the U1 that I'm looking for, which is P. So P is 0.2, which is 1 over 5. So that is how you do for 1 part 2 over here. The reason why I purposely include this in the mock paper is because this is one of the hardest. It is one of the hardest, and I would like you to know this technique. Okay. Okay, I didn't put it in the practice tutorial intentionally because I want the practice tutorial to be relatively standard questions. So yeah, let's move on to question number 2. Another sequence V1, V2, V3 is such that for all n greater than or equals to 1, Vn plus 2 minus 2 Vn plus 1 plus Vn equals to k, where k is a constant. So let Wn equals to Vn plus 1 minus Vn for n greater than or equals to 1. Explain why the sequence Wn is an arithmetic progression. Okay, to show that something is an arithmetic progression, we just have to show that the term after, okay, Wn plus 1 minus the term before, Wn, is a constant. Then we can show that it is an arithmetic progression. So Wn plus 1, okay, Wn, right, is Vn plus 1 minus Vn. Wn plus 1 is Vn plus 2 minus Vn plus 1. And then we have Vn plus 2 minus 2 Vn plus 1, then plus Vn. And then notice that, oh, this is exactly this, which is k. And it's a constant. So indeed, the Wn is an arithmetic progression because the term after minus the term before is a constant. Okay, so that's for question number 2 over here. Now, moving on to question number 3. A sequence is defined by Tn plus 2 equals to Tn plus 1 plus Tn, with T1 equals to 3, T2 equals to 1 for n greater than or equals to 1. Another sequence is defined by Rn equals to Tn plus 1 over Tn for n greater than or equals to 1. Now, part A, find T4. So we know that this is given from the question, right? Then we just say, hey, when n equals to 1, we start from the smallest. We have T3 equals to T2 plus T1 equals to 1 plus 3 equals to 4. And then when n equals to 2, we have T4 equals to T3 plus T2 equals to 4 plus 1 equals to 5. So we are done over here. We have found that our T4 equals to 5. 1 mark. Now 3b, show that Rn plus 1 equals to 1 plus 1 over Rn for all n greater than or equals to 1. So first thing first, we want to show this, right? Now, what you can do is we only have this information, so we start from here. Given that Rn equals to Tn plus 1 over Tn, we have, hey, Rn plus 1 should be Tn plus 2 over Tn plus 1, right? Agree? So basically replace the n here with n plus 1. And then now, Rn plus 1 is equals to, now Tn plus 2, okay, if you look at the question here, is given by Tn plus 1 plus Tn, okay, over Tn plus 1. Now you split this into two fractions, is 1 over Tn plus 1. And then we noted that, hey, Rn is Tn plus 1 over Tn, which means that 1 over Rn is Tn over Tn plus 1. So that means that this Tn over Tn plus 1 here is equals to 1 over Rn. So, yep, we are done showing it. So it's just a matter of playing with this equation, the equation, and then, yeah. And then replacing n over here, you know, with n plus 1. Like, these are the techniques that you need to know how to do. Right, 3c, we have, it is given that Rn converges to a limit L, find the exact value of L. So when this question appears, right, it's one of the easiest. So since Rn is convergent to L, it implies that convergence means that, hey, as n becomes very big, okay, your Rn becomes L. So if Rn becomes or approaches L, then Rn plus 1 also approaches L, right? So given the equation Rn plus 1 equals to 1 plus 1 over Rn, then we can say that we can replace the Rn plus 1 with L and Rn with L. So it is equals to L equals to 1 plus 1 over L as n tends to infinity. Now we manipulate this equation, we get L squared minus L minus 1 equals to 0. We apply the quadratic formula, we get L equals to 1 plus square root 5 over 2 or 1 minus square root 5 over 2. And we have to reject the 1 minus square root 5 over 2 because it's negative, because Rn must be more than 0. So this is from the question over here. Okay, Rn must be more than 0. Okay. No, why is Rn more than 0, right? If you take a look. Okay, Rn is what? Tn plus 1 over Tn, right? Okay. And if you notice that, hey, all the terms in this sequence here, right? If you notice, they are all positive. Okay. Let me repeat that again. Because T1 equals to 3 and T2 equals to 1. Agree or not? So any term after T2, T3, T4, T5, T6, right? You just keep adding the previous two. So you keep adding the previous two terms to get the next term. So if the previous two terms are already positive, the next term by adding the previous two terms will also be positive. So all the terms in this sequence for the T will always be positive. And if Rn is defined by Tn plus 1 over Tn and Tn plus 1 is positive, Tn is also positive, okay, then that means that Rn is positive for n greater than or equals to 1. So we know that, hey, Rn must be more than 0. So we reject this negative for the L, and this is the only answer. Okay, so when the question say that Rn converges to a limit L, then you need to know that Rn plus 1 approaches L, Rn approaches L. So you replace Rn plus 1 and Rn both with L. Right, 3D. A third sequence Un for n greater than or equals to 1 is an arithmetic sequence with first term 5 and common difference 2. D. Find the least value of n such that when you do the summation from k equals to 1 to n of uk, okay, I want the minimum n such that this is greater than 930. So for this question over here, we noted that this sequence un is an arithmetic sequence with first term 5 and common difference 2. So what we do here is, noting that this is an arithmetic sequence, right? So basically, this summation over here is just u1 plus dot 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 plus un. So noting that this is a arithmetic sequence, then what we do over here is we use the sum of an arithmetic sequence. That is, hey, there are n number of terms over here. We divide it by 2 and then use the formula bracket bracket 2a, 2 times the first term. Your first term u1 is given to be 5. And then the common difference is 2, right? So 2 times 5 plus n minus 1 times the common difference 2. So this is greater than 930. And then you simplify this, you will get n bracket n plus 4 bracket to be greater than 930. Then from GC, okay, from GC, we have this. So what you do is you go back to the original mode for a GC mode, and then you use function, and then you press y equal, then you press y equals to x bracket x plus 4 for n bracket n plus 4 bracket, and then you press second graph, you get this table, you scroll down. So the least value of n, in order for this summation to be greater than 930, you notice that, hey, when n is 28, is 896. Still not greater than 930, but when n is 29, then it is 957 for n, which means that it's greater than 930. So minimum n, least n, enough for it to be greater than 930 will be 29. And that sums up this topical paper on recurrence relation.